Hello, you are welcome to my class today. My name is Dr. Kingsley. In this class today, I will be taking chemical kinetics. What is chemical kinetics? Chemical kinetics is a branch of chemistry that studies the rate at which chemical reactions takes place. That is the speed at which chemical reactions takes place, as well as those factors that affect the rate or the speed of reaction. It also studies reaction mechanism, that is the step-by-step pathways through which reactants are converted into products. Now, we know that the rate of a chemical reaction, the rate of a chemical reaction is equals to concentration change, that is change in concentration over change in time. That is the rate of chemical reaction. So the rate of chemical reaction will be the change in concentration. These symbols here represent concentration divided by change in time. And we also know that as reaction proceeds, the concentration of the reactant decreases with time, while the concentration of the product increases with time. That is to say, if we are given that A reacts with B, to give us C plus D, we can write the rate using this equation. The rate of the reaction for this reaction here will be equals to 1 over A, change in concentration of A. Let us take minus 1 over A, change in concentration of A over change in time. Why are we putting minus here? It doesn't mean that rates have a negative value, but the minus here is simply telling us that that A is a reactant and that the rate of reactant decreases with time. So it shows a decrease. Then this will be equals to 1 over B, changing minus 1 over B, change in concentration of B over change in time, which is also equals to 1 over C, change in concentration of C divided by change in time. And that will be equals to 1 over D, change in concentration of D divided by change in time. So you can see that when we are writing rate for the reactants, the rate is carrying negative to show that there is a decrease in concentration. That means the final concentration is smaller than the initial concentration. And when doing that, you take the inverse 1 over of the stoichiometric coefficient of that reactant. Now, having taken this, we can actually also go further to know some factors that can be used to measure the rate or the speed of reaction. So we'll go to factors used to measure the speed of reaction. Now there are several factors that we can use to measure the speed of chemical reaction. Now, number one of them is concentration. We can use concentration to measure the speed of reaction. We can use number 2, volume, to determine the speed of reaction, volume. We can use number 3, we can use absorbance to measure the rate of reaction. That is to say that from what we gave before, we say that the rate of reaction should be equals to change in concentration divided by by change in time. What does it mean? If I want to determine the rate of reaction using concentration, now as the reaction proceeds, I can measure the concentration of the reactant, a particular reactant. I can measure the concentration at different time interval. So if I measure the concentration at time 1 and I measure the concentration at time 2, it simply means that what? That my rate will become equal to concentration 2 minus concentration 1 divided by time 2 minus what? Time 1. So the concentration at time 1 is taken and the time is noted. Concentration at time 2 is taken and also the time is taken. So when I do change in concentration over change in time, that will give me the rate of the reaction. Now, apart from concentration, we can also use volume to determine the what? The speed at which a reaction is proceeding. That is the rate at which a reaction is proceeding. How do we do that? Now, let us consider a reaction as you have a CaCO3, that is a calcium triazocarbonate 4. Okay, when you heat it, it will give you calcium oxide plus what? Carbon 4 oxide, which is what? A gas. Now, because carbon 4 oxide is a gas, I can measure the volume of carbon 4 oxide that is what? Formed at different time interval. So when the time is, say, 1 minute, I can measure the what? The volume of carbon 4 oxide that is formed. When the time is at, say, 4 minutes, I can also measure the volume of carbon 4 oxide that is formed. How do I now get my concentration? I mean my rate. The rate or the speed of reaction will now become the change in volume divided by what? Change in time, which is V2 minus V1 over T2 minus what? T1. So I can use, in this case now, carbon 4 oxide, which is a gas, to determine what? To determine rate. Then the third way we can determine rate, or the factor, another factor that we can use to determine the rate of reaction is absorbance. Now, for absorbance, we know that what? The absorbance of solutions are usually directly proportional to their concentration. So absorbance and concentration goes the same way. If we remember, we know that absorbance is equal to what? Epsilon L C, where A is equal to absorbance. Okay, that we are talking about. The epsilon is equal to what? Molar absorptivity. Okay, which is a constant. Then L is what? Parts length of cuvette. Okay, when you are measuring absorbance, we are talking about what? Photospectrometer. Okay, let me come up so that you can see what I've written here. You can't see this one, right? But you can see this. Okay, very good. So we are saying that this L here, okay, is the part length of the cuvette. Cuvette is what? A small glass where you put your what? Your solution that you want to measure the absorbance. So you put the solution here. So the length of cuvette, since the cuvette length is always what? Constant. The length of cuvette, which is L, is what? Is a constant. The molar absorptivity, okay, is also what? Constant. Now, if we take this, we see that what? From this equation, that absorbance of a solution is a molar absorptivity, part length of what? Of cuvette multiplied by concentration. You can see that from here, absorbance is directly proportional to concentration. The more the concentration of a solution, the more the absorbance of a solution. And if we see that what? That concentration decreases with time as the reaction proceeds, it should also mean that what? The absorbance of a solution, okay, can also what? Decrease with time. Okay, it also decreases with time as the reaction proceeds. That means that what? I can measure the absorbance of solutions as a solution at a different time interval in order to determine the what? The absorbance. I mean the speed of the reaction. Now, from here now, you can see that concentration here is equals to absorbance over EL. That means that what? If you want to calculate the what? The rate of reaction, we know that what? The rate of reaction is equals to what? Change in concentration, okay, divided by change in time. And we know that this thing now is concentration. This can replace concentration. That means that concentration here, which is a changing, it becomes changing what? A over EL. Then divided by change in what? Time. You can see from here now that what? That my rate of reaction will become change in absorbance divided by what? Change in time multiplied by what? Multiplied by EL. Remember, absorbance changes, but EL is what? Is a constant. It simply means that what? Rate of reaction is change in absorbance over change in time multiplied by 1 over what? Over EL, which is what? Constant. Now, you can now see that what? If I measure absorbance of a solution at a different time interval, okay, that I can actually use it to what? To determine the rate of what? The rate of a reaction. Now, coming to this, we have agreed already that, okay, that before I go on, please, the absorbance of a solution is actually measured by photospectrometer. Okay, so it's a photospectrometry. Okay, we use a photospectrometer to measure the absorbance. Okay, and most of the things we measure the absorbances are those things that can absorb what? Light at what? At a particular wavelength. Okay, most of them are always what? Colored. Okay, something like a DPPH. This is what? DPPH is what? 2,2-diphenyl 1-picryl hydrazine. So that is a 2,2-diphenyl 1-picryl hydrazine. This compound is actually what? A blue what? A blue stable free radical. When you make the solution of this, the solution becomes what? Purple. Now you can react this compound, a stable compound, with what? With antioxidant, for example. An example of antioxidant is flavonoid. So if you react it with antioxidant will donate what? Electron, as is reacting with what? DPPH. As a result, the color of the DPPH changes, okay, from purple to deep yellow to light yellow and to colorless. Okay, the more the change in color from deep to light, the smaller the what? The absorbance. So we need to know that. All right, having known this, we agree from the beginning that what? That the rate of a reaction decreases with time. And also, we know that what? For reactants, rate decreases with time. But for products, okay, the rate of reaction increases with time. Note it carefully, because we can represent this in a graphical what? Manner. The rate of what? Reactants decreases with time, while the rate of products, okay, increases with time. The same thing, the concentration of reactants, okay, decreases with time, while the concentration of products increases with time. Now, if I plot a graph of concentration, a graph of what? Concentration, okay, conc, against time for reactants, what do we have? We'll have that the concentration of reactants will decrease with time. So the graph will be in this manner. Then if we are to plot for what? For products, okay, the concentration of what? Product increases with what? With time. So it will be in this format. Okay, remember, it will not increase forever. It keep on increasing until the time will come it will peak. Okay, now if I have A plus what? B to give me what? C plus what? D. Which one will represent the graph for C? Because C is a what? A product. The graph will look this way. That is the plot of concentration. Concentration, okay, of C against time will look like this. But the plot of concentration of B, okay, with what? With time will look the other way, which is what? Which is a reactant. Now, having taken this, let us go to what? Theories of reaction rates. What are the theories of reaction rates? The theories of reaction rates are those theories that are put forward to explain the rate of chemical reaction. One of the theories of reaction rate is collision theory. Collision theory. What is collision theory? Collision theory assumes that there must be a collision between the reactant particles before a chemical reaction can take place, which is to say that what? The particles or the molecules of the reactant must collide with one another before a reaction can take place. It is not all the collision that leads to what? To chemical reaction. The collision that leads to chemical reaction is known as what? Effective collision. Now, this theory holds that what? That the more the frequency of collision, the faster the rate of what? Reaction. So if we have particles of reactants in what? In a container, and they are moving with high speed, colliding with one another, the more the faster they collide, the more likely the reaction will what? Take place fast. So the faster the rate of what? Of reaction. So that is what collision theory holds. And also collision theory also holds that as reactant particles are colliding, they are what? They are gathering energy. Because if two things collide, their energy will what? Might increase due to increase in temperature. So as particles collide with one another, they build energy. That energy enables them to what? To react. Now, but there is a minimum energy that must be attained according to collision theory. Minimum energy that must be attained before what? A chemical reaction will take place as a result of collision. That minimum energy that must what? That must take place, or that must be achieved before a chemical reaction can take place, is what we call activation. Okay? Energy. Activation energy, represented by this activation energy. So that is about what? Collision theory. The more the frequency of collision, or the more the frequency of effective collision, okay, the faster the rate of what? Of reaction. Then number two, another theory of reaction rates, or theory that was put forward to explain collision, is transition states theory. What is transition state theory? Transition state theory holds that what? There must be a what? A state, that a high energy state that must be what? That must be reached by the what? By the reactant. A high energy what? State that must be attained by a reactant before a chemical reaction can what? Can take place. That high energy state is transient. It is what? Very short. A short what? High energy state that must be attained by the reactant what? Particles before what? A chemical reaction can take place. This short high energy state is what we call the transition state. If you don't call it transition state, it can also be called activated what? Complex. Activated complex. Now, this is what we mean by this. Now, if we have a reaction what? If we have energy here by diagram, and this is reaction what? Coordinates. We are saying that what? That if this is the reactant, before reactant can be converted to product, it must attain energy. So it must attain energy. A time will come that when it attains energy, it becomes what? It becomes reactant to become a product. So this is reactant. And this is what? This is a product. Okay? Now, these reactants, before they react, they will collide. As they are colliding, okay, they are attaining energy. Their energy is increasing. A time will come, they will get to the highest energy state, the highest energy state, which we call the what? The activated what? Complex. EC. Activated what? Complex. Now this activated complex is a transient what? State. Once the energy is what? Is reached, then the what? The bond of the reactant will now be what? Be broken. So that the reactant will go into product. Let's say we have a hydrogen iodide reacting with another hydrogen iodide to give us what? To give us H2 plus I2. Now, what happens is what? The hydrogen iodide, okay, react with another hydrogen iodide. As they are reacting, they build energy, and this energy takes them to the highest transient energy, which we call the what? The activated what? Complex. So this is the activated complex. It is in this activated complex that the bond of the what? Of the reactants are broken, so that the reactant can actually go into what? Into products. So that is about the what? The transition state what? Theory. Now, the last theory that we'll consider, last theory. So the third theory of reaction rates is Arrhenius theory. That is the third theory. So Arrhenius theory, number 3, Arrhenius theory. What is his theory about? He states that what? The rate of reaction is directly proportional to temperature. That means Arrhenius related what? Rate of reaction and temperature. Now, according to him, the rate constant is equals to A exponential minus EA over RT. Okay? Now K is equals to rate constant. Okay? And A is equals to collision factor. Okay? While epsilon A is equals to what? Activation energy. Activation energy. Okay? R is equals to molar gas constant. Molar gas constant. The value is what? 8.314 joules per mole. Okay? And our T is absolute temperature. So that is what? Arrhenius theory. The rate of reaction increases as temperature increases. In fact, when temperature doubles, the rate of reaction also doubles. Now, if you look at this, we want to get some derivations from this what? Equation. Now let us take the lane of what? Of both sides. Let us take the lane of both sides. That is lane, I mean natural logarithm of both sides. So you see that what? Lane K will be equals to what? Lane of exponent minus EA over RT. Now, that means that what? Lane K, okay, will be equals to. Now, for natural logarithm, we can see that what? Oh, I'm talking of lane A. Thank you. So this is A multiplied by exponent this. So it's a product. Now for logarithm, the product rule goes with what? With the addition. So this will be lane A, okay, plus lane of what? Exponent minus EA over R what? RT. Now that means that lane K will be equals to lane A plus, okay, what lane does to what? To exponent is that it cancels it. So ln will cancel exponent. So that what you have here is what? You have a minus EA over RT. So the equation becomes ln K will be equals to ln A, okay, minus EA, that is epsilon A over RT. Now, if we go further, you find out that what we have will become ln K is ln of what? A minus EA over RT. Now, if you look at, you find out that what? A is what? A constant, which is what? Collision factor. R is also what? A constant. Activation energy of a reaction is what? Is constant. The only variable that can change is what? Temperature. When you change temperature, the what? The constant reaction, rate constant changes. Okay? So that means that it depends on temperature. Now, that means under different condition of rate constant and what? And the temperature, we will see that what? That our ln K1 is equals to ln A minus epsilon naught R temperature 1. So what is changing is what? K and what? T. That is to say, under another condition, okay, we have K1 will become ln A, okay, minus EA all over RT2. All right. Now, if we take this as our equation 1 and take this as our equation 2, what we'll have, we can subtract equation 1 from equation 2. Let us subtract equation 1 from equation 2. It simply means, oh, this is a 2, K2. So if we are subtracting equation 1 from equation 2, what it means is this minus this will be equals to this minus what? Minus this. So if we do that, what we will get is what? Ln K minus ln K1 will be equals to what? Ln A minus EA over RT2, then minus, okay, what are we subtracting from it? We are subtracting ln of what? A, then minus EA over what? RT1. So we are subtracting this. Remember, we open the brackets because this multiplied by this will be minus, but this multiplied by this minus will give us a plus. That is to say that what? Ln of K2 minus ln of what? K1 will be equals to ln A minus EA over what? RT2. Then this minus log A. Then this multiplied by this will become plus, okay, EA over RT1. Now, is there anything that can cancel out? Yes. Ln A and ln A, one is positive while the other one is negative, so they will fizzle out. So we'll cancel this out. So what happens is that we'll be having ln what? K minus K2 minus ln K1 will be equals to, what we have left here is what? Is a minus EA over RT2 plus EA over RT1. So if we rearrange this, starting with plus, we'll have this to be equals to what? EA over RT1 minus, this goes inside, minus E over RT what? 2. Now that will be ln K2 minus K1. Now, there is something that is common here. EA, that is epsilon A over what? Over R, is common to two of them. So when we factor it out, we have ln K2 minus ln K1 to be equals to what? Is activation energy, okay, divided by molar gas constant into 1 over T1 minus 1 over T2. So this equation is very important, okay, because it shows us what? the the effect of temperature on what? On the constant. So now I want us to take a question from here. Let us take one question using this equation so that we can actually know how to use this equation. Now very fast we can take the equation. It says for the reaction of hydrogen with iodine, for the reaction of hydrogen with iodine, okay, the rate constant is 2.4 times 10 raised power minus 4 dm cube per mole per second at 302 degrees Celsius and 0.950 dm cube mole per second at 508 degrees Celsius, full stop. They said calculate A, the activation energy. B, we have to calculate the frequency factor. Remember, the frequency factor is what? Is A. Okay, for the reaction. Calculate the frequency factor for the reaction. And number C, they say we should calculate the rate, okay, at a temperature of 400 degrees Celsius. Now, let us look at this question. Now, we are given K1 and K2. K1 and what? And K2. Now, please, if you look at this very well, can you see when I write here? Okay, so if you look at this very well, you see that lane K2 minus lane K1 is actually what? Lane K2 divided by what? By K1. I hope you can see. Is lane K2 over K1. Because in logarithm, division goes to what? To subtraction. And this will be equals to what? Lane K2 over K1. Okay? Lane K2 over K1 is equals to EA over R into 1 over T1 minus 1 over T2. We can use this last general what? Equation. Now, if you want to do that, let me claim we are looking for activation energy. You see that in this equation, we have everything, K2 and K1. We know molar gas constant. We are giving K2 and what? And K1. What is left is what? Activation energy. So we can use what? Lane K2 over K1, okay, equals to what? Activation energy of our molar gas constant into 1 over T1 minus 1 over T2. So we are having lane of our K2 is what? 0.950 over K1 is what? K1 is 2.4 times 10 minus what? 4. Okay, that will be the activation energy we are looking for. Molar gas constant is 8.314. Then into temperature 1 is what? 302. We add what? 273 to it. If we add 273, okay, to it, it will be giving us the value, okay, of 575. 575. That is 1 over 575 minus, when we add 273 to what? To 508. The value I'm having is what? 78. Okay, 781. 781. Now, having taken this, okay, the only thing that is left for us is what? Is activation energy. If you divide this over this, okay, when you divide, take the natural logarithm, it will give you a value. Then simplify this and make what? And make activation energy the subject of formula. Because of time, the activation energy Okay, from what I have here is a 149, okay, 767 joules per mole. Okay, that is the activation energy. Now the next thing we are to get what? Number 2, the frequency factor. That is frequency of collision. Now what do we do? For frequency of collision, we can take lane A, okay, is equals to what? Lane K1, okay, plus EA over what? Over RT. We can use this equation. If you like, you can use what? Lane A is equals to what? Lane K2 over EA all over RT. If you are using K1, you use what? T1. If you are using K2, you use what? So if we come up here, our lane A, okay, will be equals to lane of, what is our K1? Our K1 is 2.4 times 10 raised by what? Minus 4. Okay. Then plus our activation energy. We've gotten activation energy as 14976 then divided by 8.314 multiplied by what? The temperature T1. So our T1 is 575. So now from here you will get what? You will get your A to become equals to what? 23.0142. So that is the answer. What did I do? Simplify this side. Take the lane of this, divide this and add together. When you add together, for you to get A, you take antilog, okay, of what we have here to get your A. Then number 3 say we should calculate what? We should calculate the rate constant at temperature of 400. So we can use what? We can use lane K3 over K2, okay, is equals to EA over what? Over R into 1 over T2 minus 1 over T3. So if we use this, okay, we know what K2 is. We already have gotten this. So the temperature that we are using now for T3 is 400. So if we substitute all the values, we can get what? We can get K2. Now, thank you very much. You have gotten some tips about what? Chemical equilibrium. In my next class, I'll be discussing what? The rate law. You have to see what? Rate law, the different orders of reaction, okay, first order, second order, third order, fractional order. You see what? Reaction mechanism. So that will be in my next class. Now, please always do good to what? To subscribe, share my video and like. Thank you very much.